Another approach for finding centroids is to use the method of integration, and this is a very effective method when we know the function of the shape. It's not a nice shape, but we know some function for it. We can then use the method of integration to solve for it. So you see we will use this portion of the equation here. Let's take a look at an example. In this example, we have two equations that are defining this yellow shape. This equation here for this is y equals 1 plus x, and the bottom one, of course, is y equals 1 plus x squared over 5. And we want to find the centroid of this yellow shape. So again, we're going to use these equations, and if we look at the bottom, this integral on the bottom is actually just the area of that shape. So how do we find that area of that shape? Let's look in on that. If I zoom in on that shape itself, and if we draw a small element for this shape, I'm going to draw a very small sliver, a very small horizontal sliver. And I want to add up all these shapes as we go across, or integrate from 0 to 5 in this case. So to be able to do that, we have to look at this shape and find out what the area is of this small sliver of a shape. And we can zoom in even more. If we look at that, we have essentially the width of this shape is our value here. That is dx. It's a very small shape, right? And if I then need the height, so I can find the area of this, right? What is this height? Well, if I look at this, if I knew that, let's just say this point was 3 and this one was 2, right? The height would be the difference of the two, so 3 minus 2, so it would be 1. Well, that isn't what we have in this case. What we have, though, instead is we have these equations. So if I take the equation that I know from up above, oops, sorry about that. If I take the equation from above and subtract the equation from below, I will have that height. Okay, so this height then, if I use those two equations, is going to be y top. I'm going to call that top with a t, and this one bottom with a b is y top minus y bottom, or I will have y top, which is 1 plus x, minus 1 plus x squared over 5. I can combine this to be x minus x squared over 5. That is this height here. Okay? Okay, so now we have our width and our height of that little segment, and now we want to integrate that to find the overall area of that part of the curve. Okay, so my integral of dA from 0 to 5, my little element dA, 0 to 5, is my height, which is my x minus x squared over 5 dx. That's my width. Now I can just integrate this and solve for the area. This will be x squared over 2 minus x cubed over 15, evaluated between 0 and 5. And if I do that, I will come up with a value of 4.167 inches squared, because it's area. So that's the easy part of this, and this value then is used for both y bar and x bar. But if we go back to our equation again, the harder part of this is solving for this x tilde and trying to figure out what that is. So let's look at where we are now. X tilde, again, for our problem, is the distance from the centroid of this little segment, right, x tilde, to the y-axis. In our case here, x tilde is equal to x. That isn't so bad this time. All right, so we have, again, then for our numerator, an integral of 0 to 5 of x tilde dA, or 0 to 5 of x, because x tilde is x in our case, of x minus x squared over 5 dx. This is then equal to 0 to 5 of x squared minus x cubed over 5 dx. We integrate this. This then becomes x cubed over 3 minus x to the 4th over 20, evaluated between 0 and 5. And if we do that, we will find that our numerator then for x bar is 10.42 inches cubed. So x bar equals our, again, x tilde dA over the integral of dA, in our case, is 10.42 inches cubed divided by 4.167 inches squared, and we get for x bar 2.5 inches. Okay, now we have to find y tilde. I'm going to go to this next screen to kind of blow this up and see if we can keep it clear. So I'm going to take this segment, I'm going to make it a little wider for us, and we're looking for this centroid. And y tilde is the distance from the centroid of that shape to the y-axis. So that's our y tilde. Okay? So let's think about that. If I knew this was 3 again, and this was 2, we know again that height is 1, and we know that this distance from here, in our case, would be 2.5, right? If we had actual values. And that we find really from, how do we do that? How did we do that? We found that knowing that we can take our y top, so again our y top and our y bottom. If we add the two together, it's really the average of those 2 points, so divided by 2. So in our case, y tilde is going to be the sum of the two, 1 plus x, plus our bottom, which is 1 plus x squared over 5, divided by 2. If I simplify this, we get 2 plus x squared over 5 times 1/2. Now we need to go back to our equation again for finding the numerator, which is the integral from 0 to 5 of y tilde dA. So again, 0 to 5. Y tilde we have up above, which is 2 plus x minus x squared over 5 times 1/2. And then dA, again, remember in our case, was x minus x squared over 5 dx. Now we must integrate that. First, we'll simplify the center part. Okay, so we can simplify this to 0 to 5. And if we do the algebra, the basic algebra in there, we get x plus 3/10 x squared minus x to the 4th over 50 dx. We integrate this, we get x squared over 2 plus 1/10 x cubed minus x to the 5th over 250, evaluated between 0 and 5. We quickly evaluate that. This will then equal, we have 25 halves plus 125 over 10 minus 3,125 over 250. This will equal 12.5 inches cubed. So last, we want to find our y bar. Again, we have in our numerator this 12.5 inches cubed. Our denominator was the area that we had solved earlier. That's the same for both of these, inches squared, and our y bar equals 3 inches.